Welcome. This is the last lecture of the lecture series Digital Economy and Data Analytics. My name is Eik van Vuren, and today we are going to talk about an interesting topic, and that's the topic of neural networks and deep learning. That's going to be, as I already said, the last topic of this lecture series, and you could say that it's probably not the least important topic. And the reason behind that is because of the fact that neural networks actually did receive quite a lot of attention in the last couple of years. And a lot of people might actually even think that neural networks as well as deep learning, by the way, I'm going to assume that deep learning and neural networks are exactly identical things. What a lot of people actually think is that neural networks and deep learning are in fact, the same as artificial intelligence and machine learning. Well, that is not completely true, because of the fact that we have already seen during this lecture series that there is much more than just neural networks and deep learning. We have been looking at things as lasso and ridge, and also at tree-based methods, and these methods are actually quite often used in artificial intelligence. However, still it is the case, of course, that neural networks and deep learning, they are used quite a lot in artificial intelligence. For example, at the moment that we're going to think about face recognition is usually done by using neural networks. And that's also true at the moment that we're going to look at the very popular nowadays large language models. Also, these are completely related to, say, neural networks. So therefore we should realize that, neural networks are important. In order to start with neural networks, even though neural networks are seen as extremely fancy these days, at the moment that you're going to talk about neural networks, then it seems to be the case that everybody in the world does know these days what neural networks are. I don't think that that's completely true, because of the fact that a lot of people just know about the word neural networks, but they don't exactly know what neural networks in fact are. And at the moment that you would like to describe neural networks, then you should take into account that for you as econometricians, it can be described simply as a particular form of a nonlinear regression model. So that is to say that at the moment that we're going to look at neural networks, they are actually nothing else as a very specific parametric form of a nonlinear regression model. So here we are talking about completely parametric form. So in that sense, for you as econometricians, that might seem a little bit old-fashioned, because of the fact that these days, non-parametric analysis is usually much more interesting. But we should take into account that neural networks, they are very parametric. This having said, you should take into account that they are also very flexible, and they are also very complex. So even though a lot of people do seem to know something about neural networks are very complex to understand. And that is probably also the reason why probably today is going to be a little bit harder than most of the other, say, lectures that you have already seen from me. But let's start with the simple things, and that is the first question that arises is, where does the name neural networks actually come from? Of course, we have neural networks and deep learning. I myself actually think that deep learning might be a better name than neural networks, but the question arises, where does neural networks derive its name from? Well, it is because of the fact that they were originally seen as able to mimic the human brains. I find that myself usually a little bit complex, very difficult to understand, and I also find it actually quite confusing. That's probably because of the fact that I'm not a medical doctor and not a brain surgeon, so therefore I don't probably know that much about, say, medicine and how human brains actually work, but we should take into account that actually, therefore, I do have the idea that it's much easier to understand, not through the idea of trying to, explain it through the working of human brains, well, even though a lot of books actually try to do that, I'm not going to do that. Instead, what I'm going to do is that I'm going to look much more at a statistical approach with respect to neural networks. But that also brings me to another thing, and that is that, well, what we should realize is that, one of the problems actually that has been a long period of time a problem in terms of artificial intelligence is that for a long period of time, artificial intelligence didn't make that much of progress. And the reason behind that was mainly because of the fact that, well, for a long period of time, actually maybe even since the start of the computer, then people already started to think about artificial intelligence. And for a long period of time, well, artificial intelligence was actually seen as, that part of computer science in which we try to, have computers do things that usually are done by human beings, and that is, of course, fine. But what I was also thought for a long period of time was that it might be interesting then to actually, have, or at least that we then have to have computers also think like us. And that is has been for a long period of time a persistent misconception. At the moment that we would like to make computers do things like that we do ourselves, then of course we don't have to actually make computers to think the same as we do. And even though, as far as I know, and I already said that I'm not a medical doctor and I don't know exactly how human brains work, but even though we do not actually know ourselves how human brains work, we do of course know how computers work. And computers actually work differently than human brains. And therefore we should take into account that for a long period of time, artificial intelligence wasn't essentially making a lot of progress. And the main reason behind that was essentially because of the fact that they were having the idea that they had to do exactly the same things as what comes from human brains. But you should take into account that that is not necessarily the case, of course. And only since, artificial intelligence, or people working in artificial intelligence, started to realize that, we should not do that. That is the period of time, and that started, I think, in the 80s. At that moment in time, then we actually do see that a lot of progress has been made. And in that sense, we can compare that quite a lot with, airplanes. Ever since, I would say, existence of human beings, we always have been trying, to fly, of course. And for a long period of time, we have been trying to do that by, for example, making wings at our arms and trying to fly like a bird. Well, that didn't work, of course. And only since we, more or less 125 years ago, decided that we are going to use, say, real machines, and are going to use those machines in order to fly. Ever since then we have airplanes and we are able to fly, but not like birds. And that's an important thing that you have to take into account. At the moment that you think about artificial intelligence, then you should think about computers, essentially about statistics, and not so much about trying to mimic the human brains. Well, that was a very long introduction to neural networks, but I'm not going to now directly discuss neural networks themselves. What I'm going to do is that I'm going to still stick a little bit more to an introduction, but that's to say that I'm going to first of all look at a particular theorem, and that is so-called Kolmogorov's theorem. The nice thing with respect to this Kolmogorov theorem is that it's actually quite nice introduction to the neural networks that we are going to discuss later on. And this Kolmogorov's theorem actually says that every continuous function g star, that is to say that any continuous function from 0, 1 to p to the power p to r, this is of course then a function which is p-dimensional, and where we are going to have that, say, all the different x values that we're going to have, they are allowed to take values in between 0 and 1. So this is the domain of that particular function, and it's a p-dimensional functions, but the domain is only in between 0 and 1. And then we're going to state that if p is larger than or equal to 2, then that particular function can always be written as g star x is equal to the sum, well, it's a sum from g is, or j is 1 to p plus 1. Then we're going to have a function fj here, and well, this fj function is going to be evaluated in another sum, and that is going to be a sum from I is 1 to p, where we're going to have the sum of h ijxi. Well, this looks a little bit difficult, and therefore it might be best to look at the most simple example that we can actually think about, because of the fact that well, p must be larger or equal to 2. That means, of course, that p equal to 2 is going to be the most simple case. And what do we get then? Well, then what we're going to get is g star x is equal to, well, then f1 evaluated in h11x1 plus h21x2 plus f2 evaluated in h12x1 plus h22x2 plus f3 evaluated in h13x1 plus h23x2 plus f4 evaluating h14x1 plus h24x2, and then finally we have f5 evaluated in h15x1 plus h25x2. Well, what this actually means is that this is of course still quite complex, but what it actually means is that this function j star x is actually nothing else as a sum of what you could say univariate function. So you should realize that unlike this function j star x, which is of course dependent on both x1 and x2, well, these f1, f2, f3, f4 and f5 functions, well, they are univariate. They only depend on one particular variable. But that's neither x1 or x2. It's more like a mixture of x1 and x2, because of the fact that that depends on, in fact, these h functions that we have over here, where we have that, say, in this case for the function f1, well, it depends actually on x1 through the function h11, and it depends on x2 through the function h21. But in the end, it is just this thing that we have over here, well, is just, say, a one-dimensional variable. So it's just a one-dimensional outcome, which means that also the functions h11 and h21, they are, say, univariate functions. They only depend on one particular variable. Well, for h11 it's x1, and for h21 it's x2. Well, more generally, of course, we are going to have that, say, the h1j functions, they are going to depend on x1, and the h2j functions, they are going to depend on x2. We can actually write this a little simpler because of the fact that this is still quite complex, of course, but we can write this a little bit simpler at the moment that we're going to define this zjx function that we've over here. If we are going to define it as h1jx1 plus h2jx2, then what we can do is that we can write it as, well, g star x is then simply equal to f1 evaluated in z1x plus f2 evaluated in z2x plus f3 evaluated in z3x plus f4 evaluated in z4x, and then finally we have here f5 evaluated in z5x. We can even make it simpler than that, because of the fact that what we can do in the end is that we can even, well, use here or define here a function hjx being equal to, well, fj evaluated in zjx, and then at that moment in time, well, g star x is simply equal to a1x plus a2x plus a3x plus a4x plus a5x. Well, this is still quite complex, but we should take into account that Kolmogorov theorem can be best illustrated by a simple picture. Here we have then on the left hand side, we have the two, I would say, inputs to our g star x function. Our g star x function is here at the right, and there are two, of course, inputs that are the variables, and we see that we have two variables. We have an x1 and an x2. Well, then what we can do is that we can then go on with respect to this very first node, this upper node that we have over here, and what we essentially see is that this upper node is in fact sourced by two functions. It's first of all sourced by H11 that is actually more particularly sourced by this x1. It's it's H11 evaluated in x1, and then it is also sourced by the variable x2, but then through this function H21 that we have over here. More in particular, of course, what we are going to get is this variable z1 that we've over here, this one-dimensional variable z1 that we've over here, which is actually nothing else as H11 evaluated in x1 plus H21 evaluated in x2. Then we get this z1 that we've over here. Well, that z1 is then transformed towards an a1, and that goes actually through this function f1 that we've over here. So f1 transforms z1 into a1. Well, and then we should realize that we can also do that with respect to all the other nodes. For example, if you're going to look at this node that we've over here, also this node gets inputs from x1 and x2, but again that now goes to two different functions, namely h12 for x1 and h22 for x2. More in particular, of course, this z2 that we have over here is going to be equal to, well, h12 evaluate x1 and h22 evaluated in this x2 that we have over here. Then we get z2, and again that z2 can be transformed into an a2 through this function f2 that we have over here. Well, we can also do that, of course, with respect to all the other nodes that I have over here, and then what we're going to get is that we're going to get a1, a2, a3, a4 and a5 in the end. Well, then the only thing that we still need to do is that we have to add up these a's that we have over here in order to get finally our g star x. That is the idea behind the Kolmogorov theorem. Well, now what we should realize is that we can also say this in words. So this is just an illustration of Kolmogorov's theorem, but what does Kolmogorov's theorem mean in words? Well, in words, the Kolmogorov theorem states that we can always write a p-dimensional function in terms of a sum of 2p plus 1 univariate functions. Well, that sounds like a very great idea, of course, because of the fact that, probably you had a little bit the same as me when you started university, that, at the moment that you were in the first year calculus courses, then the p-dimensional functions, or at least multidimensional functions, were introduced. And I always find myself multidimensional functions very difficult to understand. Of course, still maybe a two-dimensional function is easy to understand, but already a three-dimensional function becomes much more difficult to understand, and a 4, 5, 6-dimensional function becomes really difficult to understand, of course, or almost impossible to actually understand what is going on there. And therefore, Kolmogorov's theorem actually says that we can always transform, say, any kind of function. Well, that's not completely true because of the fact that we still have some restrictions. The function has to be continuous, as well as that we have to have this domain that we have over here. Well, that final thing is not that restrictive because of the fact that we can always, say, normalize a function in such a way that it can only take values in between 0 and 1. But what we should take into account is, in fact, that we can always, according at least to Kolmogorov's theorem, we can always write any kind of multivariate function into a sum of univariate functions. And then what we should realize is that these univariate functions are evaluated in a sum of univariate functions with respect to all the p variables of the original function, because that's exactly what we do over here. What we're going to do is that we use here, say, that these univariate functions f that we have over here, they are evaluated in a sum of these h functions that we have over here. So therefore you should realize that in that sense Kolmogorov's theorem, at least in theory, seems to be a very interesting, say, a theorem, and that could actually be used, of course, could potentially at least be useful practically, because of the fact that then what we can do is that we can always make a very difficult function, a very highly dimensional function, into a sum of, say, univariate functions. However, you should realize that even though this is of course very interesting and it's going to be, I would say, the input of neural networks, there is of course a problem. And the problem, or the main drawback with respect to Kolmogorov theorem, is that it actually is only, well, you could say, a proof of existence. That is to say that you can show that there exists a, say, combination of these f functions as well as these h functions, that this relationship may actually, or makes this relationship to hold. What we should take into account as well is that it doesn't give us any clue of what these functions actually are. And that means that, for example, of course, for very simple functions, this may be quite easy to find out, these functions that we have over here, but that is only going to be for very trivial, very simple functions. But for complex functions, it's going to be completely impossible to find, in fact, these functions f as well as this function h in such a way that this is going to be the case. So it's just a proof of existence. These functions do exist, but what they are, we have no clue about it. Take into account that in a machine learning context, this is even more problematic, and the reason behind that is because of the fact that, well, in a research or in a machine learning context, we should take into account that this g star x, well, it is even unknown to us. G star x is an unknown function for us, so therefore, well, generally, of course, even in the case that g star x is known, then it's going to be very hard to find these f and h's, but we should take into account that, well, we even don't really know this, say, g star x. That's the problem that we generally have with respect to machine learning. Well, neural networks try to solve actually both of these problems that I've just discussed by, well, to assume a particular kind of function. So we are simply going to assume functions for, say, parametric functions for this for these f's that we have over here, as well as with respect to the h functions that we have over here. But at the same time, what we're going to do is that we're going to increase flexibility by increasing the number of nodes that we have over here. So in Kolmogorov theorem, the number of nodes that you only need is, in this case, at the moment that p is equal to 2, then you only need 5 different nodes over here. In general, of course, 2 times p plus 1 nodes that you have at the moment that you have p different axes. But what we could do is that we could, of course, include many more nodes over here in order to create more flexibility. Well, the number of nodes that we are going to use in a, say, neural network context is usually called the width of the network. So that is simply the number of fj functions that we are going to include. Well, then the question arises, what kind of functions are you going to assume then? Well, we will start with respect to the h functions. For the h functions, we simply are going to assume linearity. So that means that for the two-dimensional case, we can simply write our zjx functions that we have introduced before, and remember that they are equal to h1 jx1 plus h2 jx2. We can now simply write them as w1 jx1 plus w2 jx2 plus bj, where j, of course, now is going to run from 1 to p1, where in this case p1 is going to be the width of the network. If we would like to do this more generally for, say, any value of p, so for any amount of features that we're going to have, well, then we're going to get this zjx function, and that is then, well, in this particular case, of course, nothing else as the sum over, say, all the hij functions, where the sum actually runs from I is 1 to p0, where p0 actually is simply equal to the p that we had so far, so the number of features, but we're going to call it now p0 in order to distinguish it from our p1 that we have introduced at the previous slide, which is the width of the network, say the number of, say, f functions that we're going to introduce. Well, and what is that then? Well, that is then in this case equal to the sum, again from I is 1 to p0, of wij multiplied by xi plus bj, where again j is going to run from 1 to p1. Well, what we could do is that we could also use here matrix notation. So if we are going to define b as a vector with the elements bj that we have just introduced over here, and w is going to be a matrix with elements equal to the wij that we have over here, then at that moment in time we can write this as a vector valued function zx, so no longer the zj axis of course, but it's going to be a vector valued function which essentially has as elements simply the zj axis that we've over here from j is 1 to p1, and that can be directly written as, well, w transposed times x plus b. Here, by the way, and that is another time vocabulary, well, in neural networks there's actually a lot of vocabulary, even more than in other parts of machine learning, but we should realize that this W matrix that we have over here is usually called the weight matrix, sometimes also simply called weights, and this B that we have over here, this vector B that we have over here, is usually called the bias vector, or sometimes simply called the bias. And take into account that even though this is called the bias, this has nothing to do with the bias in a normal sense at the moment that we are thinking of standard statistics. Well, then the question that arises next is that what are we going to now use for our fj functions? Well, our fj functions are typically chosen to be either a logistic function. By the way, another thing that I have to say over here is that these fj functions are usually going to be assumed all the same. So we're not going to assume like f1, f2, f3, f4 to be different, but we are going to assume that they have all the same, say, specifications. And one of the choices that we can make is that we are going to choose fjz, well, which we will denote by sz, to be a logistic function. And probably you already know what a logistic function is because of the fact that it's always a function that has xz in the numerator, and we divide by 1 minus xz. This is just the, say, standard logistic function that you might already know of the logit model. Well, this is a very popular choice with respect to the fjz functions, but there is an even more popular choice, and that is the choice of the rectified linear unit, usually called the ReLU function in machine learning. And well, that is actually nothing else as the following function, fjz, which is again denoted by sz, is now simply equal to, well, it's equal to z, so it's a linear function simply, but multiplied by an indicator function that indicates that z must be larger or equal to 0. Well, now another type of vocabulary is that these s functions that we have over here, they're usually called activation functions in, say, neural networks. Well, then the question arises, how do these functions actually look like? Well, here the y-axis are by the way not exactly identical to each other, but they look as follows. Here we on the left hand side have the logistic function. Well, it has a very famous shape because of the fact that you should realize that the logistic function can actually be seen as a distribution function, and any kind of distribution function has this, well, essentially this S shape that we have over here. Well, then the ReLU function, well, it has another kind of shape because of the fact that it's simply equal to 0 up to, say, 0. And then, well, at the moment that we are going to have values of x larger than 0, well, then it's actually nothing else as a, say, 45 degrees line here from, say, 0 onwards. Well, even though this ReLU function looks very simple, and you might actually say probably too simple, this ReLU function actually has an important benefit that actually we don't find with respect to the logistic function. That is to say that the logistic function has one particular problem, and that's the problem that we usually call saturation. What does saturation mean? Well, what you should realize is that because of the fact that this is a distribution function, it implies, of course, that it cannot take values higher than 1, and that implies that if x becomes larger and larger and larger, well, that's not that much the case here yet, but at a particular moment in time, the derivative of this, say, logistic function that we have over here, it will become close to 0. And what does that mean? Well, that means, of course, that at the moment that we, for example, are going to change, well, then maybe it's best to go back to this slide that we have over here. Then at the moment that we are going to change the values with respect to z, if z already is large, so this z1 that we have over here, then at the moment that we are going to change the values of z1, well then actually, well, a1 is not going to change at all. And the reason behind that is because of the fact that, well, this f1 function is already completely flat. And therefore it actually doesn't change at the moment that we are going to change this z1 value that we have over here. And that of course implies that essentially the g star function is not going to change either by, say, changes with respect to this z1 that we have over here. Well, that is something that we don't like, and therefore we should realize that that is actually a problem with respect to the logistic function, but with respect to the ReLU function, at least at the moment that we have values larger than 0, well, then we do see that actually the ReLU function is always increasing. Well, then what we're going to get is this neural network that we have over here. This is a very, or I would say the simplest neural network that we can actually think of. What we should realize is that this neural network has already 3 different layers. It looks a lot like the, say, network that we have already seen by illustrating Kolmogorov theorem. It has 3 different layers. It usually has an input layer, it has a hidden layer, and it has an output layer, which actually is only, well, the g star x that we have over here. In the input layer we do have our input, so to speak, and that is well, our x1 and x2, say our features that we have. And then at the moment that we're going to look then at the hidden layer, well, these hidden layers, they're sorted by, in fact, say x1 and x2, but also in fact by these well, these weights that we have over here, as well as the bias term that we have over here. And like what we had with respect to the Kolmogorov theorem, we should realize that first of all, at the moment that we're going to look at this very first node that we have over here, and we are going to concentrate now on z1, well, z1 of course is sourced by, well, first of all x1, and it is done in this case by simply multiplying x1 with w11. Well, but it's also sourced by x2, and that is in the way that we simply have to multiply w21 by x2. So z1 simply is the sum of w11 times x1 plus w21 times x2. Well, we still have one additional part, and that is of course this b that we have over here, or more in particular this b1 that we have over here. So in total what we're going to get is z1 is w11 times x1 plus w21 times x2 plus this b1 that we have over here. That is our z1, and then our, say, activation function is going to transform this z1 into an a1. Well, we have exactly the same thing at the moment that we're going to look at the second node that we have over here. Then we can concentrate on z2. z2 of course is sourced by x1 through this weight w12 that we have over here. More in particular, we get w12 times x1 plus of course, well, w22 times x2 plus of course this final bias term b2 that we have over here. Well, we can actually go on now of course with respect to all the different nodes. We can go on here to the third node, the fourth node, etc., up till the, well, p1 node, the width of this particular network that we have over here for whatever of course p1 is. We should realize that this dashed line actually just indicates that there are many more nodes, and of course also weights etc. that we have over here. And then the final thing here, at least in this network, that we still have to do is that we have then to, like in Kolmogorov theorem, to add all these a's that we have over here together, and then we get our final output, and that is going to be our g star x that we have over here. What we would like to do is that we would like to, this is not really a neural network yet, what we would like to do is that we would like to introduce a little bit more notation, and in addition to that, we also need to introduce a little bit more, I would say, to this neural networks. The first notation that I'm going to use is that we are going to write the inputs in the input layer no longer as x's but as a's. They are going to be denoted by a0. So that implies that, for example, a01 is going to be x1, a02 is going to be x2, etc. And then what we are going to do as well is that we even are going to allow the output layer to have its own bias and weight. So so far what we have been doing is that we simply said, like, well, then the output g star x is simply nothing else as the sum over the a's that we have over here. But we could do that as well, of course, in a weighted way, in the sense that we are going to give weights to this sum that we have over here, and then we can even add a bias term to that. So that is still something that we are going to include into, say, our analysis. But then, of course, what we could even do is that we could use an activation function, a separate activation function for this g star x that we have over here. That is now going to be this s2 function that we have over here, which can be different from the s function that we already had over there. So that's still a thing that we can, of course, do. And then in addition to that, well, this s2 function, by the way, that is usually going to be a logistic function. And then well, what we can do is that we can also then rewrite, of course, the weights and the biases. We can actually give them also the original ones that we already had over here. So these ones that we have over here, as well as these ones, the sets and the A ones that we have over here, as well as the bias that we have over here, we can actually write them also with respect to their subscripts, the indices. Actually, here we are going to do that with respect to an index 1, and here with respect to an index 2. So then we are going to get our, say, final neural network. It almost looks like what we already had before, but a little bit different notation. So we don't have x1 and x2 anymore, but now we have a01 and a02. We still, of course, have our bias, but now that is denoted by b1. And here we have our weights, but take into account that, for example, the weight W11 is now written as W111. And, well, then, for example, Z1 is now written as Z11, and A is written as A11. And then we have here also new notation. The, say, activation functions in this hidden layer are now going to be denoted all by S1. But here, up till here at least, we have exactly the same ID as what we had before. But now we are going to have a little bit difference over here because of the fact that now what we're going to see in order to get the output layer is that we also have here weights. Here W21, W22, W23, W2 up till P1. And then we also have this single bias over here. This is just one number which is called B2. And then we are going to take all that together, and well, the weighted sum in this case, together with this bias term over here, is going to give us our Z2. And then that Z2 is going to be transformed into an A2 by this activation function that we have over here, and then A2 is exactly the same as G star. Now that we have our first neural networks, take into account that the calculation of G star goes from the left to the right. In order to look at that, take into account that we actually start with the calculation with respect to this input layer that we have over here, starting with the features, and then we go through the hidden layer towards the output layer in order to finally get the computation of G star. Well, that implies that we can, well, summarize this in the following steps. At the moment that we go to here to the left, then we are going to see that first of all, in the input layer, we are going to define the A0s. That is to say that we are going to, first of all, redefine the axis into these A0s. That is to say that the first feature, x1, is going to be labeled as A01. The second of it, x2, is going to be relabeled as A02, etc. So that implies that at the moment that we then are going to look at the very first step, well, very generally we are going to set A0i to be equal to xi, for I is going to run from 1 to p0. Then in the second step, well, what we would like to do then is that we would like to then go from, say, this input layer towards the hidden layer. More in particular, what we would like to get is these Z1s that we've over here. And we do already know how to calculate these Z1s because of the fact that they are sourced, in fact, by the W1s, first of all, by this one, for example, by W111, and as well as W121, as well as, say, the bias term B11 that we have over here. More in particular, what we're going to get is that the Z1j's, they are going to be equal to B1j, the bias term, plus the sum running from I is 1 to P0 of W1ij multiplied by A0i, for j is from 1 to P1. So that implies that we now are already here in this hidden layer. However, then what we would like to have is the A1s. Well, we do already know how to get these A1s because of the fact that that simply implies that we have to evaluate the function S1 into, well, this Z1 that we have over here. So more in particular, what we now need to do is to, well, calculate the A1j's by evaluating the S1s. So the A1j's are going to be equal to the S1s evaluated in Z1j, for j is equal to 1 till P1. Well, that implies that now we are already over here, and we do now know already the A1s, but now we would like to calculate this Z2 that we have over here. Well, that again implies that we are going to source this Z2 by, in fact, well, essentially this W's, these weights that we have over here, multiplied, of course, with respect to the A1s, and in addition that this B2, the bias term that we've over here. So therefore, Z2 is going to be equal to B2 plus the sum from I is 1 to P1 of W2i multiplied by A1i. So that implies now that we are now already in this output layer at Z1. Well, then the final thing we would like to get is, of course, A2. And we do already know how to get A2 because of the fact that A2 is actually nothing else as the function S2 evaluated in Z2. So that implies that then we have A2, and A2 is of course exactly equal to G star. So therefore the only thing that we still need to calculate is G star X is of course equal to A2, and that is simply equal to S2 evaluated in Z2. So here we do see that what we are going to do here is that we do the computation from the left to the right, from the input layer towards the output layer, through, in fact, through the neural network. And because of the fact that we go through the neural network in a forward way, going from the input layer to the output layer, we usually give this a name, and the name that is given to that is feed-forward propagation. I would like now to go on with the next topic, and that is the topic of how now to set the parameters. We should realize that we have many parameters that we still need in order to do this feed-forward propagation that we have over here. Take into account that, well, all these, calculations that we have over here, well, they actually need some parameters. Well, not the first one, of course, because of the fact that we do already know the features over here, so we can directly calculate the A0s that we have over here, but we cannot directly calculate the Z1s, for example, because of the fact that that depends on, in fact, all the W's as well as the B's that we have over here. In addition to that, we also, of course, at the moment that we would like to go from the hidden layer to the output layer, well then also we should realize that then we actually need all these parameters that we have over here. So therefore the question arises, how we're going to set those parameters in order to be able to calculate to do in fact the feed-forward propagation. Well, before I'm going to talk about that, the first thing that I would like to ask myself is how many parameters do we actually have? Well, in that sense, we should realize that we have actually two steps in our case because of the fact that we have now in our neural network two steps. That is, first of all, a step from the input layer towards the hidden layer. There we have a lot of, say, parameters, but we also, of course, have parameters here from the hidden layer to the output layer. But let's start with respect to the first one, the input layer towards the hidden layer. Well, there what we should realize is that we there have, first of all, we have the W's. How many W's do we have? Well, that actually depends on the number of features. In this case, of course, 2, but in general, that is equal to P0. And that's going to be multiplied by the number of nodes that we have in the hidden layer. That is, in this case, equal to P1. So that implies that we are going to get, well, P0 times P1 of these W's that we've over here. But that's not everything yet, of course, because of the fact that we still have the bias terms. And how many bias terms do we have? Well, we have exactly P1 of them. So that implies that from the input layer to the hidden layer, the total number of, say, parameters that we have is simply equal to P0 times P1 plus P1. Well, now in our case, we do know that P1 is only, or I'm sorry, P0 is only equal to 2. So the number of, the number of features that we have is only equal to 2. And we haven't said anything yet about P1, but suppose that we have now a P1 which is equal to 12. Well, then at that moment in time, we can directly calculate the number of parameters that we need to estimate in the first stage. That's namely equal to 2 times 12 plus 12 is 36. But that's not all the parameters that we have, because of the fact that we also have to look at the parameters in the second stage, in this stage from the hidden layer towards the output layer. How many of them are there? Well, that's of course equal to P1 for, say, this part, the weights that we have over here, plus 1 of course, because of the fact that we have now only one bias term. So that implies that in total for the second stage from the, say, hidden layer towards the output layer, we have in total P1 plus 1, say, parameters. And then the question of course arises, what would we have then in our case? Well, again, if we are going to assume that P1 is equal to 12, as we did over here, then in total we're going to get then 13 different parameters, which means that in total we are going to have 49 different parameters. Take into account that this is not that much yet for a neural network. That's essentially because of the fact that we haven't set P0, we have P0 actually in this case quite low. But take into account that for a very simple neural network, this is already into the hundreds or maybe even into the thousands or 10,000. So therefore we should take into account that this could actually be quite large in the end, of course. Now, of course, the question arises, how are we going to estimate all those parameters? Well, for that, the first thing that I'm going to do over here is that I'm going to introduce this vector theta. It's the parameter vector that we are going to look at. And, well, that vector theta is going to be decomposed, or is going to be composed of a number of different elements. First of all, we are going to have our, say, matrix W1. W1 is here the weights of, say, of the step from the, say, input layer to the hidden layer. These are all these, well, in this case, red and blue arrows that we have over here. So that is W1. Then, in addition to W1, we also have W2 over here. Well, W2 is the vector of weights from, say, the hidden layer towards the output layer. If we go back to this picture that we have over here, it's all these, say, weights, these arrows that we have over here. That is W2. Then, in addition to that, we also have B1. B1 is a vector of bias terms from, say, the input layer towards the hidden layer. These are these green, arrows that we have over here. And then finally we have B2, and B2 is actually nothing else as, say, this number, this scalar that we have over here, the bias term that we have from the hidden layer to the output layer. Well, take into account that we can take them all together. Well, this is actually not that great mathematical notation because of the fact that we cannot combine, of course, a matrix W1 with a couple of vectors as well as a scalar over here. So therefore, the first thing that we need to do is that we officially have to flatten actually this matrix over here in order to make it a vector. I'm not going to go too much into the technical details in order to do that, but we will just use this notation theta that we have over here. And then the simple thing that we next are going to do is that we're now going to estimate our vector theta by this theta hat. And the way we are going to do that, as usual, is that we're going to do that by minimizing our training risk. This is now going to be our training risk, which apart from yi and xi, depends of course also on this theta that we have over here. Well, take into account that this is actually nothing else as a non-linear minimization problem. So therefore we can solve this in terms of a standard nonlinear minimization problem. Of course, this doesn't have a closed form solution, so what we actually have to do is to try to solve this numerically. Well, there are many methods in order to do that, but what we are going to do is that we're going to solve this with respect to steepest descent. Well, I'm going to later on say what steepest descent actually is, but take into account that in order to do steepest descent, what we need is that we have to calculate then the first order derivative of this risk function that we have over here. And take into account that in order to calculate the first order derivative of this risk function that we have over here, we have to take the first order derivative of this loss function that we have over here for all the individual observations that we have. So that is the first thing that we actually need to do. Well, for that I'm going to introduce a little bit of notation. I'm going to write down ci theta for the loss function, evaluating yi, xi, and theta. And then what we need to do is to take the first order derivative of this ci theta with respect to theta. Well, that we can do recursively, and that also has a very special name, and that is usually called backpropagation. I would like now to discuss this backpropagation. And what we should realize is that backpropagation is actually nothing else as recursively using the chain rule. And what we essentially would like to do is that we are going to do this backwards, which essentially means nothing else as that, with forward, say, or feed forward propagation, we were calculating G star by starting actually from the input layer to the hidden layer towards the output layer, but with respect to backpropagation, in order to calculate the first order derivative of our, say, loss function, then what we are going to do is that we're going to do it the other way around. We actually start over here at the output layer, and then we are going to try to get, say, the first order derivatives first actually of, say, these parameters that we have over here, and then we are going to go through the hidden layer to these parameters in order to calculate the first order derivatives of these final parameters that we have over here. Well, in order to do that, the first thing that I would like to do is that I would like to first of all look at the relationship between, say, our ci that we have defined on the previous slide, this ci that we have over here, which is nothing else as a loss function evaluating yi, xi, and theta. Well, that we would like to look at the relationship between ci and the z2, so this z2 that we have over here. Well, in order to do that, we are going to immediately use the chain rule, and what we're going to do is that we're going to say that this first order derivative of ci with respect to z2 is equal to the first order derivative of ci with respect to g multiplied by the first order derivative of g with respect to z2. Well, we should realize that this first part, the first order derivative of ci with respect to g, well, that actually depends on the loss function. That actually depends on the loss function that we have, because of the fact that then what we need to do in order to calculate that, what we have to do is to take the, say, first order derivative with respect to the loss function and with respect to g. Well, that depends, of course, on the choice of the loss function that we're going to make. At the moment that we are going to have a continuous case, so if in the case that we're going to look at regression, then we do already know that we're going to use this quadratic loss function. Well, in the case that we would have looked at classification, then generally we're going to use the 0,1 loss function. Well, that one cannot be used here because of the fact that that one is not differentiable. Instead of that, what we usually do is that we're going to use a so-called cross-entropy loss function. Well, I haven't talked too much about that, and at this moment in time it's actually not that important, but you should realize that even in the case that we are going to do, say, classification, we are going to assume at least that the first order derivative of the loss function with respect to g is available. But we don't know what it actually is because of the fact that it depends, of course, on the specific case that we're going to look at. So we just keep it like that. We just keep the first order derivative of ci with respect to g. But we do know, of course, what the first order derivative is of g with respect to z2, because of the fact that we do know that actually, well, the thing that we are going to have is that g is actually nothing else as, say, z2, well, better to say s2 evaluated in z2. So that means that if we take the first order derivative, it's actually nothing else as the first order derivative of s2, well, evaluated, of course, in z2. And that implies that what we can do is that we can simply realize that this first order derivative of c with respect to z2 is nothing else as the first order derivative of ci with respect to g multiplied by the first order derivative of s2 with respect or evaluated in z2. Now the nice thing that we do know is that z2 is actually equal to b2 plus, well, w2 transpose times a1. This is just the, say, vector notation that we are going to have with respect to z2 that we have already been calculating with respect to feed-forward propagation. Well, this is quite nice because of the fact that this also gives us the opportunity to directly look at the first order derivative of ci with respect to b2 as well as the first order derivative of ci with respect to w2 transpose. Well, let's start with the first order derivative of ci with respect to b2. Well, again, using the chain rule, can be written as the first order derivative of ci with respect to z2 multiplied by the first order derivative of z2 with respect to b2. And then we should realize that based on this, well, we do already know this part over here because of the fact that that was actually already there. So therefore we can simply substitute that in. And then the only thing we still need to do is to multiply this with respect to the first order derivative of z2 with respect to b2. Well, that's actually quite simple because of the fact that that is, of course, nothing else as equal to 1 because of the fact that this thing that we have over here is actually nothing else as 1. So therefore we should realize that we have to multiply this, of course, simply by 1, and that implies that we can just keep it like that. Well, then we can also look at the first order derivative of ci with respect to w2 transpose. Well, then again, we are going to use the chain rule by writing first of all the first order derivative of ci with respect to z2 multiplied by the first order derivative of z2 with respect to w2 transpose. Well, this thing, again, we know that is this part that we have over here, and this thing that we have over here, well, directly looking here, we directly see that that's actually nothing else as the vector a1 that we have over here. And therefore, in total, what we're going to get is, say, the first order derivative of ci with respect to g multiplied by the first order derivative of, say, this s2 function evaluated in z2 multiplied by this a1 that we have over here. So that gives us already the first order derivatives of, say, b2 and this w2t, so transpose. So that actually already gives us the, say, first order derivatives of these parameters that we have over here. Now, you might of course say like, well, but still there are a lot of things which are known to us, such as this z2 and this A1 that we've over here, but take into account that these are actually already calculated for a particular set of parameters. They can already be calculated by using feed-forward propagation. So that implies that we do actually already have these first order derivatives that we have over here. But now let's look at, say, the first order derivatives with respect to this step that we have over here from the input layer towards the hidden layer. Well, for that, the first thing that I'm going to do is that I'm going to first of all look at the relationship between Z2 on the one hand and this Z1s on the other hand, and take into account that that is necessary because of the fact that here what we did was that we looked at the relationship between, say, C and Z2, and we then looked at how Z2 was related, or how actually these parameters were related to Z2. Well, then we can do it here as well, but then first of all we have to know something of the relationship of Z1 with respect to this Z2 that we've over here. So therefore, the first thing that we're going to do is that we're going to look at the relationship between Z2 and Z1. We're going to look at the first order derivative of Z2 with respect to Z1. Well, again, here we can use the chain rule because of the fact that this is the first order derivative of Z2 with respect to A1 multiplied by the first order derivative of A1 with respect to Z2. Well, and that, well, the first thing we can do is this thing that we have over here. That one is pretty simple because of the fact that on the previous slide we have already seen what Z2 actually is. So therefore, taking the first order derivative of Z2 with respect to A1, that's of course simply this matrix, this W2 transpose, well, vector that we have over here. So therefore we should realize that now what we're going to get is this thing that we have over here. However, still what we need to do is that we have to look at, say, the first order derivative of A1 with respect to Z1. Well, take into account that this A1 that we have is actually nothing else as, well, S1 evaluated in Z1, because of the fact that that is something that we already know from this hidden layer that we've over here. What the hidden layer in fact does is bring Z1 towards A1 by, in fact, well, evaluating S1 into Z1. So therefore A1 is equal to S1 evaluated in Z1. So that implies that the first order derivative of A1 with respect to Z1 is actually nothing else as, well, first of all, of course, taking the first order derivative of S1 evaluated in the first element, say Z11, well, of course, then S1, or the derivative of S1 evaluated in the second element, Z12, etc., up to, of course, the, say, first order derivative of S1 evaluated here in Z1P1. So that is this factor that we have over here. It's a gradient, and therefore what we can do is that we can define that gradient here simply by this D1 that we have over here. Well, then the next thing we can do is that we can then realize that this first order derivative of Z2 with respect to Z1, I have repeated that over here. That was this thing over here, and I repeated it here. But now we can simply realize that that's simply equal to, well, the vector W2 transposed multiplied by D1. Well, then what we can do is that we can then also look at the relationship between Ci and Z1. Well, then another time using the first order, well, actually the chain rule, we should realize that that is of course nothing else as the first order derivative of Ci with respect to Z2 multiplied by the first order derivative of Z2 with respect to Z1. Well, we do already know what this is because of the fact that we have been calculating a long time ago, actually all the way over here. So that one we do already know, and then we have to multiply that with respect to the first order derivative of Z2 with respect to Z1, and then we do know as well because of the fact that that actually is this thing that we've over here. I actually kept this notation. I could have of course substituted the first order derivative of Ci with respect to Z2, but I actually kept it just over here just to realize that we have already calculated that before. And then we should realize that then Z1, well, we do know what Z1 is because of the fact that the vector notation of Z1 is actually nothing else is that it's B1 plus the matrix W1 transpose times A0. And that implies that we now can directly calculate the, say, first order derivatives of ci with respect to b1, but also the first order derivative of ci with respect to w1 transposed. Well, let's first start with the first order derivative of ci with respect to b1. That's again using the chain rule equal to first order derivative of ci with respect to z1 multiplied by the first order derivative of z1 with respect to b1. Well, now we should realize that this thing we have already been calculating, that is this thing that we've over here, so we can simply substitute that into, and then the first order derivative of z1 with respect to b1, well, that's actually nothing else as, say, a vector of ones. This is of course a vector, so we get a vector of ones. Well, we don't have to denote that here, so we can simply have that thing that we already had. So we don't have to multiply this, of course, any longer with this thing that we have over here because of the fact that that is just equal to 1. Well, then the first order derivative of ci with respect to w1 transposed, well, that again using the chain rule is equal to the first order derivative of ci with respect to z1 multiplied by the first order derivative of z1 with respect to w1 transposed, and then we are going to get that that is equal to, well, again, dc terms that we have over here that we get from there, and then multiplied by the first order derivative of z1 with respect to w1 transposed. Well, that's of course simply equal to this a0 that we have over here. So now we actually do have all the first order derivatives of ci with respect to any of the elements of theta, any of the parameters that we already had. Well, then the final thing that we still need to do is that we have to realize that we have to take the first order derivative of this risk function that we have over here. Let's use a little bit of notation. Let's say that that risk function can be denoted by, say, c theta, and that's of course nothing else as this thing that we have here, but it's also of course nothing else in our earlier notation as this thing that we have over here. It's the sum with respect to the i's of the ci theta divided by n. Well, then taking the first order derivative of c with respect to theta isn't that difficult anymore. It's simply now 1 over n multiplied by the sum from I is 1 to n of course these first order derivatives that we have over here, but take into account that these are the first order derivatives that we have been calculating on the preceding slides. Now, in order to train the model, that means estimate the vector theta, we usually are going to use steepened descent. Well, that is something that I already said before, and take into account that we could have used other kinds of methods, like for example Newton-Raphson or quasi-Newton methods, but instead we're going to use this steepest descent because of the fact that that is the one that is most often used in order to train a neural network. Well, this implies that we first of all have to set a rough guess with respect to theta. So we have to have a starting value with respect to theta, and that we usually are going to do by using small random values for the weighting matrices and positive values for the bias terms. The reason behind that is because of the fact that at least for the ReLU activation functions, we should try to make all the z terms positive. The reason behind that is because of the fact that if they're not going to be positive, then we are going to be on the, say, horizontal, the flat, say, part of this ReLU activation function. Take into account that that is problematic. And the reason behind that is because of the fact that then at that moment in time, at the moment that we are going to have z's, for example the z1s that are going to be negative, it implies that even at the moment that we're going to change the w's, then nothing is going to change with respect to the a1s that we have over here. So suppose that z11 here is going to be negative, then at the moment that I'm going to change the w's or the beta terms that we have over here, then even though z is going to change, well, nothing is actually going to change with respect to a11 because of the fact that we are on the flat part of this activation function, and therefore also nothing is going to change with respect to finally this g star that we have over here. So therefore what we would like to have is positive values with respect to the z's that we have over here, at least these z1s as well as this z2 that we have over here. How can we make that for sure? Well, with respect to the, say, features that we have over here, we don't know that because of the fact that either the features could be positive or negative. So we do not know exactly what actually we should choose, whether we should take a positive value for the w's or whether we should take a negative value. But what we do in order to be sure is that we take actually quite small values, either positive or negative. And then what we're going to do is that we're going to take positive and somewhat larger values with respect to the bias terms. Then we know for sure that what we're going to get is something which is going to be positive all for these Z1s, and we're going to do exactly the same things with respect to the weights and the bias term that we have here for Z2. So that's the first thing that we're going to do. And then what we're going to do then next is that we are going to do an updating, and the updating is actually as follows. First of all, we are going to, give this guess a name. We're going to give it a name being equal to theta 0. And then the next thing we're going to do is that we are going to repeatedly update the thetas according to the following, namely theta t is going to be equal to theta t minus 1 minus alpha t multiplied by the first order derivative of c with respect to theta. That's exactly that first order derivative that we have just been calculating over here. Well, and then this alpha t, that is a thing that we usually call the learning rate, and it's usually a value in between 0 and 1. And this learning rate, we're not going to do that. Well, we have already seen with boosting that we also have a learning rate, but the learning rate is here a little bit different. And this is usually what we set, simply somewhere in between 0 and 1. And usually we set it a little closer to, say, 0 than to 1. And, the idea behind steepest descent is actually quite easy. What we're going to do is that we're going to run into the direction in which we essentially are going to go down with respect to the function. That's the idea. Well, then the thing that you should take into account is that this is, of course, a gradient. So it has multiple values, of course. It has multiple inputs, actually, of that particular vector. But suppose that we are going to look at one particular parameter, and we're going to see that, for example, the first order derivative of that particular parameter is going to be negative. Well, then, since it's negative and we have here a minus term, that essentially means that we're going to update that particular parameter in such a way that we're going to make it larger. Well, that makes sense, of course, because of the fact that at the moment that we're going to see that we go actually down with respect to the function, at the moment that we, say, are going to make the value of the particular parameter larger, well, then at that moment in time, we should actually do that. We should actually go in that direction in order to, decrease the value of this c function that we've over here, because of the fact that we wanted to minimize that c function. Well, take into account that, of course, it's also possible that the first order derivative of c with respect to theta for a particular parameter is going to be positive. Well, in that case, what you should do is not actually run into the direction of making, say, the parameter value larger, but then actually you should do it the other way around. You should actually make that parameter value smaller. So that's the whole idea behind steepest descent. Well, then what we are going to see is that at the moment that we are going to do this, then at first, of course, the first order derivative of c with respect to theta is still quite large, but it will become smaller and smaller and smaller over time at the moment that we do more steps in terms of steeper descent. Well, we will never ever get to 0, but what we can do is that we can at least stop at the moment that the inner product of this first order derivative that we have over here is going to be very, very small. Then at that moment in time, we do know that we are very, very close towards, say, our minimum, and then we can actually stop. Now there is one problem with respect to steepest descent, and that is that it can be actually quite slow. And the reason behind that is because of the fact that the calculation of the first order derivative of this c with respect to theta, we already know that that's this thing that we have over here, that can be extremely time consuming, especially at the moment that we are going to have, say, a very large data set, so data sets that run into the millions or even more than that. And at the moment that we have very large models, which means that we either have, say, many different, say, features, or we are going to have, say, many different parameters. So therefore we should realize that at that moment in time, this may actually take you a very, very long period of time. Well, in order to admit that, what we usually see is that, these kind of methods, the neural networks, they're usually not trained directly by steepest descent itself, but they're trained by something else. They're trained usually by stochastic steepest descent. Well, to understand the idea behind stochastic steepest descent, suppose that we see the whole training sample as our population. So that means that we essentially are going to assume that any observation that we have in our training sample has a probability of occurrence equal to 1 over n. Well, what does that mean? Well, that means, of course, that the first order derivative, this first order derivative that we have over here, can be seen actually as nothing else as the mean of the population derivative. And the reason behind that is because of the fact that, well, if we have this as the full population, then of course we can write this as a sum, but of course it's nothing else as the population mean if we already assume that this is the full population. So therefore, we can then realize that this thing is of course equal to that thing that we've over there, and well, with the notation that we have seen before, it's also equal to the mean of this first order derivative that we have over here. But based on that, what we can do is that we can try to get a good estimator of this thing that we have over here. Well, for that we can use the analogy principle. We do already know for a long period of time that at the moment that we are going to have what we usually call a population mean, then we can, well, try to estimate it by its corresponding sample mean. So therefore, suppose that we're going to have a random sample of the original, say, training sample that we have of a size equal to large n. And even though we write here large n, we're going to assume that this large n is much smaller than the small n that we have for the number of observations that we have in our total training sample. Well, then what we can do is that we can then, well, estimate this first order derivative that we have over here by, in fact, the average, the sample average over this random sample that we've over here. And because of the fact that we should realize that this is a random sample where yi star and xi star, they're simply randomly sampled from the original training sample. Well, we usually call this a so-called mini batch, and take into account that because of the fact that this is the so-called sample mean of the corresponding population mean, that means of course that this is going to be a consistent estimator of that thing that we have over there. That's in this case actually quite trivial because of the fact that we should realize that at the moment that we are going to increase this large n that we have over here towards the size of this small n that we have over there, well then at that moment in time you should realize that what we have here, the right hand side, is exactly equal to what we have over there. So therefore we should take into account that of course this is a consistent estimator of this thing that we have over here. But we can then use actually this as an estimator in order to use it for our steepest descent. So we're not going to do our steepest descent now with respect to, say, the full sample, but we're only going to do that with respect to this, say, random sample. So we're only going to use, say, the random sample in order to calculate this first order derivative. So in terms of our steepest descent, we're just not going to use steepest descent as we already did, but we are going to replace this, say, first order derivative as what we had before with the estimate of the first order derivative. Well, take into account that we are going to use a new sample for every iteration. So we're not going to do this just for, say, the same randomly sampled values for every iteration, but instead we're going to do a new sample for every iteration. We actually have to do that because of the fact that otherwise we're not going to use the full sample. If we would actually use every time exactly the same random samples, well then at that moment in time we would in fact do essentially, well, standard steepest descent, but we would have done actually that on a very smaller training sample. We just would have then reduced the training sample. That's not what we want. Instead, what we would like to do is that we still would like to look at the whole sample, and therefore what we're going to do in order to, well, still get the whole sample is that we're going to calculate this thing or estimate this thing over here every time on a new random sample. Well, there is a drawback of this method that we have over here. Even though it's much faster, it also has an important drawback, and that is that because of the fact that this is an estimator, it does have noise. And that implies, of course, that based on the random sample that we are going to have, well, we can sometimes see that we are going to have a very low, say, first order derivative, as we have over here, but then in the next step, we might actually have a completely different random sample, and then the first order derivative is going to be much larger. That implies that what we're going to see is that at the moment that we're going to start this, say, stochastic steeper descent, is that we typically are going to go down very quickly with respect to the first order derivative, the estimated first order derivative, but then at a particular moment in time, it's going to stabilize and it's actually going up and down, up and down, and up and down, based in fact on the particular random sample that we're going to use. And it will never ever get very close towards zero. Therefore, instead what we are going to do is that we're not going to stop at the moment that this, say, estimator becomes equal to zero, because of the fact that that will never happen. We simply stop after a certain very large amount of iterations. Well, what we usually do then is that we do not count the number of iterations that we have of the steepest descent, but for the stopping process we usually count the number of epochs. Then the question of course arises, what is an epoch? An epoch equals the amount of iterations needed to sample the full set of observations. That, for example, implies that if we have 100,000 observations and a mini batch is of the size equal to 1,000 observations, that it means that one epoch is going to be 100 stochastic steeper descent iterations. So that implies that if, for example, you say like, well, I'm going to do 10,000 epochs, that means 10,000 times 100 stochastic steeper descent iterations. Now I would like to go on with the last topic of today, and that is multi-layer neural networks. In a very old paper, Minsky and Peppert in 1969, they showed that a 3-layer neural network has very poor predictive power. So the neural network that we have been looking at so far, that only has an input layer, a hidden layer, and an output layer, it has very poor predictive power. And therefore, people actually never use this kind of neural network. Well, therefore, instead, the neural networks that are usually used in practice, they do actually have multiple hidden layers. And the number of hidden layers is usually called the depth of the neural network. So the number of, say, hidden layers that we're going to have is the depth of a neural network, whereas the number of nodes that we have per, say, hidden layer, that's usually called the width of a neural network. Well, in order to give you an example of a, say, neural network that has a couple of different hidden layers, here we now have our, well, neural network that we already had before, but now with 2 different hidden layers. That implies that we still have our input layer, we still have only 2 different features, and this part is still exactly the same as what we already had before. But now what we're going to have is that we have here the first hidden layer with P1 different, say, nodes, but we also have a second hidden layer that has P2 hidden nodes. And we should realize now that, well, now we are going to have many more, say, parameters, because of the fact that all these, say, arrows that we have over here are also now going to be new weights, and they essentially are going to be, say, new, say, parameters. And also here, this, say, hidden layer has also its own bias term, here the bias term B2 that we have over here. And then finally we have our output layer. Well, that is still exactly the same as what we had before. Now we have these weights over here, and we also have the bias term that gives us a Z3, and then through this activation function SC, we are going to have our A3, and that is going to finally be our, say, function G star. So we should realize that now we have a much more complex, in fact, neural network, and take into account that now I only have 2 hidden layers, but of course we can increase the number of hidden layers to, say, 3, 4, 5, etc. Well, take into account that this also implies that the number of parameters that we're going to get is going to be much larger than what we had before. If we're going to look at this simple, or still relatively simple, neural network with just 2 hidden layers, then the question arises, how many parameters do we have? Well, still, of course, in the very first, say, step that we have over here from the input layer to the hidden layer, well, we still then have P0 times P1 plus P1 different parameters. However, we should take into account that at the moment that we're going to then go from the first hidden layer to the second hidden layer, well, then what we're going to get is P1 multiplied by P2 plus, say, these P2 different, say, parameters that we have over here, the P2 bias terms that we get actually from this B2 that we have over here. And then finally we should realize that then we still are going to get, say, P2 of these weights over here plus 1 for the situation in which we are going to go from the last hidden layer towards the output layer. Well, that means in our case that suppose that we are going to assume that both P1 and P2 are going to be equal to 12. Well, then the number of parameters that we're going to get is 2 times 12 plus 12 plus another time 12 times 12 plus 12 plus 12 plus 1. That is going to give me 205 parameters. Well, take into account that this still is actually not that many parameters at the moment that we're going to look at a neural network. We should realize that very simple neural networks usually already have in the thousands of different parameters, and in many cases you actually get more than 10,000, or maybe you could actually have in the 100,000s or in the millions of different parameters. Take into account that I actually have asked today ChatGPT how many parameters there are actually with respect to ChatGPT. Well, strangely enough, ChatGPT didn't know it herself, but what we should take into account is that she at least indicated that there are, say, more than 1 trillion different parameters actually trained in ChatGPT. So that implies that you're going to have many, many different parameters in, I would say, realistic neural networks. And the question, of course, arises, how can you actually take control of those parameters? Well, take into account that we can do that by regularization. We can also here use standard rich or lasso regularization, and the idea is exactly the same. However, in this case, of course, what we're going to get is not, let's say, a linear minimization problem, but instead we get a nonlinear linearization problem with respect to this loss function that we've over here. So therefore, we simply are going to get, say, our training risk, but now what we're going to do is that we're going to add a penalty term to that. Well, in the case that we're going to look at ridge regularization, it's going to be equal to lambda times theta t times theta. So this is now going to be my, say, ridge regularization term. Well, and take then also into account that the regularization parameter lambda, well, we usually are going to set that, or we're going to determine that by using cross validation.